Hi everyone, and welcome back to part 3 of the Dead Earth game development series. Now, over the next couple of videos we're going to investigate Unity's navigation and pathfinding systems, as well as examine the topic of pathfinding in general. Now, you may be thinking that this is a weird place to start in my Dead Earth development, but as I said in my previous video, I want to be faithful to the process that I went through when first developing Dead Earth. Now, when tasked with developing this game, I was pretty confident that the other elements of the game, things such as the first-person controller, the weapon systems, the inventory systems, and the various scripted sequences would not be a problem for me, as I have done many similar things in Unity already in other projects. However, I hadn't really been involved in any projects that used Unity's navigation system, so I really wanted to understand what the limits of those systems were and to make sure that they were fit for my purposes. Also, I knew that I would be stepping outside of my comfort zone a little bit with the sheer amount that I was going to be relying on Mechanim in this project. That's Unity's animation system. Mechanim is not new to me, but I hadn't yet worked on a project that required so much of its functionality. Furthermore, I knew that I wanted to use Mechanim to control the movement of my characters by utilizing the root motion stored in animations. The problem with this approach is that both Unity's animation system, when used in this way, and Unity's navigation components in their default condition assume control of the character's transform during their updates. This can cause a race condition where both systems are fighting to update the transform of our character based on entirely different criteria. Now, we're going to be looking at how I resolved this issue a little down the road when we start using Mechanim and writing our AI behaviors, but for now we just need to understand fully how to utilize Unity's navigation and pathfinding subsystems so that these later situations can be resolved easily and without friction. Fortunately, Unity provides a fairly robust navigation and pathfinding system that is extremely easy to use and pretty much does all of the hard work for us. Now, while I could easily start right now showing you how to use it, I would like in this video and perhaps the next to have a more general discussion on pathfinding in games. While we don't need to write our own path search algorithms when using Unity, because its nav mesh agent component will do this for us, it's still a very good idea, I think, to understand as much as possible how the components and tools that we are using work behind the scenes. This will allow us to understand how to use it efficiently and how to bend its default behavior to our will. Furthermore, Unity's navigation and pathfinding systems do have some big limitations that come from its need to be generic and fast. Now, while I haven't found this to be the case yet during the development of Dead Earth, I have not ruled out entirely that further down the road, either on this project or maybe on projects such as The Rising, we may need to implement our own simple pathfinding systems as well to deal with very specialized unit types. Now, if this does turn out to be the case, we're definitely going to be glad that we spent the time now learning how this stuff works. But if that turns out not to be the case, it doesn't matter. This is very cool knowledge to have and something I think every game developer should have in their knowledge arsenal. So what is pathfinding? Well, first of all, let me just set some terminology here. When discussing entities in games that process pathfinding data and update their positions and reasoning based on that data, we refer to them as agents. Therefore, each zombie in our game can also be referred to in pathfinding terms as an agent. In fact, when we wish to give our zombies pathfinding behavior in Unity, we will need to add to each zombie Unity's nav mesh agent component. This component will query the scene graph and calculate a new path on demand. It will then store and use this calculated path to steer the agent towards its current target. Now, on a complex game level, like those found in today's first-person shooter games, we can't simply face our agents towards their targets and then just tell them to march in that direction until they reach their goal. Moving our agent from A to B as the crow flies will almost definitely have them walking through solid objects such as walls, furniture, or even entire buildings. We are going to need our agents to compute a navigable route through our complex scene. In Dead Earth's city scene, for example, we are going to have agents that need to plot routes from one side of the city to the other. They're going to need to know all of the streets and roads to walk down and what objects to avoid as they do so, or indeed, if the target that we've set for that agent is even reachable at all. Now, a naive first solution might be to consider an entirely dynamic and runtime solution, using, for example, trigger volumes. When those triggers are intersected by other objects, we could compute the obstruction's position and generate a modified velocity vector for our agent that steers us around the object. This works fine for local obstructions. In fact, this is very much a local avoidance system, and it's not so different to how I handled the AI cars in GI Racing. It's also very similar to how Unity's navigation and pathfinding systems deal with dynamic object avoidance at runtime. That is, a similar method is used to help multiple agents avoid each other as they're navigating their paths. However, this system of local avoidance just does not work for complex scene geometry at all. Using purely this system, we can imagine how an agent could head towards its target completely unobstructed for quite some time, only to find much later along its route that it has navigated down a dead end and the target is now unreachable. It's clear that much more detailed analysis has to be done on the scene to plot a sensible, intelligent route, and this has to be known ahead of time by the agent. It's possible, for example, that in order to reach the target, an agent may well have to spend the initial part of its journey heading away from its goal. We can see here that with detailed analysis of the scene, the agent would know that it had to first travel away from the target to get out of the dead-end passage in order to start moving towards its goal. Now, detailed analysis of anything at runtime sounds expensive, and you'd be right. Therefore, pathfinding subsystems generally compile data about the scene at development time, such as in the Unity editor, for example. This data can then be searched at runtime by agents to find the path it needs to take to reach its goal much more quickly. Modern pathfinding systems usually comprise of at least 4 parts or subsystems. The first part of the process is the building of a navigation graph. This happens at development time, and whilst it can be done manually, is usually something these days that is done via a tool and therefore is an automated process. And this is certainly the case with Unity. It has a built-in tool that allows us to bake a navigation graph of our entire scene with just the press of a button. Now, the navigation graph is nothing more than a data structure that describes to our application at runtime all of the navigable areas in our level, all the places that our agents can go. The remaining parts of the system are all implemented at runtime. These include path queries, steering logic, and a local avoidance system. Although we'll draw down in a bit more detail on these in a moment, path queries are basically what happens when we tell the agent to move to a new destination. It will send its current location and the destination we wish it to move to into the navigation graph and perform a search on that graph to collect all of the waypoints, all of the nodes that the agent must move along to reach its destination. Of course, once it gets this list of waypoints, it then has to do something with them, and that's where the steering logic module kicks in. It's the steering logic which is responsible for updating the position of our agents over time such that they move from one waypoint to the next until the list of waypoints has been exhausted and our agent is finally at the destination that we chose. We also have the local avoidance system. Like I said, this is really part of the steering logic, but I've separated it out here just to make explanations a little easier. The local avoidance system is purely there to make sure that when we're steering along our path from one waypoint to the next, that if there are any other agents or dynamic objects in our way, that we take a slight detour off of our route just to steer around the object before we pick up our route again and carry on as normal. So let's talk for a few seconds about navigation graphs. As just discussed, the first step in this pathfinding process is to compile all of the static elements of the scene into a graph. Now, as I'm sure many of you are aware, a graph is just a data structure that represents data and its connections or links to other pieces of data. The graph describes, for any set of objects, how they are connected or linked to one another. Each piece of data in the graph is referred to as a node, and the node may have links to other nodes in the graph. Graphs come in many different forms and can be used to contain almost any type and arrangement of data. In games, scene graphs have been used historically to spatially partition scenes to speed up collision queries, or to describe the parent-child relationships between objects in a scene. When the graph has been compiled specifically to aid in searching for valid navigation paths for AI agents, however, this is often referred to as being a navigation graph. Now, in the image on screen, we can see the interior of a small house and how this might be represented in memory as a graph. We can see that the node that represents the living room has only one connection, sometimes called an edge, and that is to the hallway node. The hallway node has three connections, however: a connection back to the living room node, a connection to the garden node, and a connection to the kitchen node. The kitchen node has two connections, to the hallway and to the dining room, while the dining room node has only a single connection back to the kitchen. What you are looking at here is a very simple scene graph, in this case a navigation graph, that accurately describes how all of the rooms in this house are connected. If our agent was in the dining room, for example, and was instructed to visit the living room, it could use this graph to perform a search out from the initial node, the dining room node, until it found the living room node, keeping track of which connections it had to travel down along the way. In this instance, we can see that performing a search on the graph would determine that in order to reach the living room, we would need to create a path consisting of 4 waypoints. We will assume for simplicity in this example that the position stored at each node is the center point of the room it represents. With the path now calculated, the agent now has to invoke its steering behavior to move itself along the path over a period of time depending on settings for speed and turn rate. The agent would head towards the first waypoint in the path, the kitchen. Once the kitchen was reached, it would move on to processing the second waypoint, the hallway. Finally, when it had moved to the hallway and that waypoint had been reached, it would process the final waypoint and its desired destination, the living room. So we can see that once we have the traversable areas of a scene compiled into a graph, calculating paths for agents in a game becomes a more generalized problem of performing specialized searches on a graph and collecting the relevant data as we go. Once we have searched the graph, the output is a set of waypoints that our agent can move along, in sequence, until the target is reached. Now, in the simple games of yesteryear, a navigation graph would commonly be created by hand, or by code in the editing environment. This could be done by simply hand placing game objects in your scene and attaching scripts to each that allowed you to set its connection to other nodes, simply by dragging and dropping game object references. Now, admittedly, that would be very time consuming for a complex level that contained hundreds or thousands of waypoints. It's also pretty common in 2D top-down games to generate the navigation graph programmatically by simply dividing the scene into a uniform sized grid, where the center point of each grid represents the node position. The good thing about a grid is that if we consider each grid square to be a node, we can compute the connections to each of its 8 neighbors easily using array index arithmetic. We might imagine, for example, a simple tool could be constructed that would divide the scene into a grid of bounding boxes. The objects in the scene could then be examined, and if any solid objects were found to be either fully or partially contained within a grid square, then that node would either be removed from the graph or set as a solid, non-traversable node. We would finally be left with a graph of just empty nodes and their connections. as a grid square would need to be considered non-traversable if any object even partially intersected it. For decent pathfinding, the grid would often have to be very granular, leading to many waypoints and therefore much larger graphs that slow the path search algorithm at runtime. The modern de facto standard in games, and a system also implemented by Unity, is to use a special type of navigation graph which is baked at development time using the actual polygon data of the game world. This is called a navigation mesh, or nav mesh for short. Using this system, a mesh is constructed of convex polygons which represents only the traversable polygons in the game world. This polygon data, however, is not just stored like a regular mesh, but is stored as a graph. Now, in the somewhat simplified diagram of the mesh that you can see on the screen, we can see that when represented as a graph, we know how the polygons are connected to each other. For example, if we know the polygon that one of our agents is currently standing on, we can find that node in the graph easily. We can then search out through its neighboring polygons, and then their neighboring polygons, and then their neighbors, and so on, until the target polygon is located. Now, navigation meshes can be built by hand in a modeling application by an artist, but this is often very time consuming for complex scenes. It is still a technique that is employed in many games, however. But it's often the case, and this is the case with Unity, that a tool is provided that can be used to bake a nav mesh automatically with just the touch of a button, and thank heavens for that. Now, navigation meshes in video games are usually credited to a guy called Greg Snook. Now, he published an article in the year 2000 entitled Simplified 3D Movement and Pathfinding Using Navigation Meshes in the book Game Programming Gems. So if you want more detail on that, do check it out. Well worth a read. Now, we're going to talk in more detail about nav meshes in the upcoming videos, but for now, all you need to know that Unity provides this method as a means of generating a navigation graph for our game levels that its agents can use at runtime. Okay, so let's talk about path queries that will be done by the agents at runtime using the compiled graph. Performing path queries on the navigation graph is the next part of the puzzle that needs to be solved. These queries are performed at runtime by the agent. So via code, we will instruct the agent to head towards a new destination. When this happens, the agent must perform a graph search to find all the relevant edges and nodes of the graph that will take us to our destination. First, the node the agent is currently contained within must be found. Once found, we begin a search out from that node along its edges into its neighbors, and their neighbors, and their neighbors, and so on. We also keep track of the nodes we have passed through along the way. Eventually, assuming the destination is reachable, we flood out into a node that happens to be our desired destination node, and our search is complete. All we have to do then is return the nodes that we have collected along the way whilst constructing the path. The output from the search is just a list of waypoints, basically just positions in 3D space that the agent then must visit in sequence to get to its destination. Of course, this searching through many nodes would be very time consuming using an unoptimized search algorithm. But you're going to see in the next video how the A-star search algorithm is used almost exclusively these days in games for path searches on navigation graphs. We're going to dedicate a fair amount of time to understanding this algorithm intimately, but for now just know that this search algorithm makes intelligent guesses during the searching of nodes to minimize the number of total nodes that have to be visited to typically a very small amount. Also, with the A-star algorithm, we are guaranteed to get the shortest path from the source to the destination, something that is also very important if the navigation of our agents is going to look intelligent. Like I said though, we're going to examine the A-star search algorithm in detail very shortly. So let's talk about the steering logic. The next part of the system is also executed by the agent at runtime in response to a path being calculated. It handles the updating of the position of the agent over time as it navigates the waypoints of the returned path. Now, in an extremely simple system, This could be nothing more than keeping the agent facing the next waypoint and updating its position at each update by some velocity to navigate along the path. As each waypoint is reached, the next waypoint is selected until the agent reaches its final waypoint and has reached its destination. Unity's NavMesh agent component, however, provides much more functionality. It allows us to clamp the speed of the agent and its rotation so the agent will not merely snap to a new orientation when changing from one waypoint to the next. It also allows us to set acceleration and deceleration parameters so that the agent slows down or brakes organically as it reaches each waypoint along the path. Unity's navigation system also allows us to configure an agent to only be able to traverse certain navigation layers and at different costs. A character, for example, might be able to navigate via swimming across a water node, but a tank or a car would not be allowed and would therefore find a different path around the water feature when searching the graph, if such a path existed. Finally, we've got the local avoidance system. Now, although I've labeled this as a separate subsystem, local avoidance is actually part of the steering logic in Unity. Now, in the case where a single agent is moving throughout the world, a search of the graph could just return a list of waypoints as previously described that we can then navigate through in sequence. However, it's quite possible when multiple agents or other dynamic objects are in the scene that blindly moving along a line segment from one waypoint to the next could cause us to collide. Therefore, in Unity, and most likely in other NavMesh implementations, the path search on the graph actually returns what Unity calls a corridor. Essentially, this is just a list of polygons from the NavMesh that the agent is going to travel along. One of the real advantages of using a NavMesh and getting back a corridor instead of just a list of waypoints is that because we don't just have line information from one waypoint to the next, but instead have polygon information, those polygons represent areas. And we also know that each polygon that is returned in a corridor describes an area that is totally traversable. So this makes it possible for Unity steering logic to modify the current velocity vector at any given frame to take a little detour from the path to avoid other agents without fear of steering us into solid geometry. The polygon areas tell us where and where we cannot go. A simplistic but useful way of thinking about it is like this. When the search is first complete, we have returned a corridor, a list of polygons. The steering logic then calculates the desired velocity for the current frame to move the agent towards the next waypoint, or corner, as Unity calls them. However, this velocity has been calculated only factoring in the static geometry stored in the navigation graph, and it may not be possible to use unmoderated. A further check is made to make sure that moving along the velocity vector would not cause it to collide with another agent or dynamic object. This is the local avoidance system kicking in. Now, if it's found that a collision would occur, then a second velocity vector is calculated to essentially repel the agents from one another. When this is blended with the initial velocity vector, and remember, the agent we are colliding with is also doing the same thing during its update, agents will essentially act like magnets with matching poles, repelling each other off their current routes only for a small amount of time until they have passed one another, and then their route can be resumed. Now finally, in Unity, the agent velocity is tested and modified further if necessary to make sure that the agent is contained within the bounds of the NavMesh. This is important to have a robust navigation system. With the final velocity agreed upon, the default behavior in Unity is for the NavMesh agent component to then update the position of the game object to which it is attached. So all of this movement happens automatically from our perspective. Okay, so looking at the time, I'm going to bring this video to a close. For those of you that know my previous work, you'll know that I have a reputation for creating monstrously long videos. So I promised GI with this course that I would reduce the video size, increase the quantity, so that we have more videos but in smaller, more digestible chunks. So in this video, we've taken a look from a high level about what a pathfinding system is and the various components it involves, and have somewhat of an understanding of how all the pieces work together. Now in the next video, I'm going to concentrate on really drilling down on the A-star pathfinding algorithm. Now, like I said at the beginning of this video, we don't necessarily need to write our own A-star pathfinder because Unity's NavMesh agent provides this functionality for us. But like I also said at the beginning of this video, it's worthy knowledge, and it's something that we may need to implement down the road if we find that we have certain units or certain scenarios for which Unity's navigation system is not a good fit. So I'm going to leave it there for now, and I'll see you in the next video.